Okay, so in the previous chapter, in chapter 4, we spent a lot of time talking very carefully about the various transformations of the plane, okay? And we concentrated at the end on focusing on the transformations that preserve distances and angles, which were the isometries, and they were mainly of two types. Well, no, we had a theorem which listed 6 different geometric types, but they mainly fell into 3 categories: translations, rotations, and reflections. And the reflections had 2 types: normal reflections and glide reflections, and so on. And we gave a kind of detailed algebraic treatment of those, and we looked at all the tools we need to kind of perform most kinds of computations with those, okay? Now, when we look at transformations of 3 dimensions, I think we're going to concentrate more on the implementation of it. So more on the view of it via matrices for the moment anyway. Because you'll see in the upcoming, not assignment 4, but assignments 5 and 6. In assignments 5 and 6, you have to work on constructing your own 3-dimensional virtual environment, okay? And the basic way that's going to work is, just as in the current assignment, you start with a basic motif, and then you move it around the plane and get it to do various things using transformation matrices. Well, in the 3 dimensions, building your virtual environment is going to work the same way. We're going to be building an environment made up of a number of basic building type shapes or building structures. These can be defined just as kind of rectangular boxes and with pitched roofs and so on, but they're defined by a set of coordinates in their own kind of object space. We'll be making this more formal later on. But you have the basic models of these buildings. But then to create your environment, you need to take various copies of these and place them into the environment. You might want some large ones, some small ones. You might want them to be rotate, all the houses aren't going to face the same direction, say. You want to pick up these basic built models of the structures and place them into the virtual environment, rotated various ways and translated to various positions and maybe scaled up and scaled down in various directions to create some kind of a realistic environment containing lots of buildings. So the main kind of transformations you're going to want to use there are translations through 3 dimensions and rotations and scalings. So these are the ones we're going to focus on now. So translation, scaling, and rotations in 3 dimensions. It will turn out that the translations and scalings are really fairly easy to describe and to deal with. There's really they're really not any more complicated than they were in 2 dimensions, except that you've got this 3rd dimension now, but you just handle that with the use of an extra component for all the vectors and so on. The rotations, however, are slightly trickier to deal with. When you're rotating in 2 dimensions, let's say you're rotating about the origin. If you've got various different rotations about the origin, for one thing, they all commute with each other. If I'm going to rotate my hand by a certain angle and then follow it by another rotation about the origin, about the center point of my hand by some other angle, it doesn't matter in what order I do the 2 rotations. The net effect is still to rotate by the sum of the angles. So all the rotations about a particular fixed point, they all commute with each other, and they all kind of, so that's one thing that makes them easy. And there's only 2 choices about how to rotate. You either go clockwise or anti-clockwise, but they're really the same kind of thing, because going clockwise is just going anti-clockwise by a negative angle and so on. So now, of course, rotations about different centers have to be handled carefully, because those won't be commutative. If you have 2 rotations about 2 different centers, if you compose those, it does make a difference the order in which you compose them. So in general, rotations aren't commutative with each other. It's only when they're rotations about the same point. Now, rotations in 3 dimensions are more complicated because there's much more, the addition of the extra dimension gives you much more freedom. A basic rotation is now no longer rotating about a point, but we now rotate about an axis. Okay? So a basic rotation of 3-dimensional space is to fix some kind of rotation axis, say this direction of the pen here. So this particular line in 3 dimensions, which is running through my fingertips here and going out in the direction of the pen. And then we can rotate the whole of 3 dimensions by some angle around that axis. Okay? So all the points on that rotation axis remain fixed because the whole of space just kind of rotates, twists around that axis. All the points on the line remain fixed, but everything else gets moved around. So we're not rotating around a point, we're rotating around a line, an axis of rotation through the space. But the point is, from emanating from any particular point, there's a whole, there's a whole sphere's worth of possible rotation axes. There's lots of freedom in the different directions that the rotation axis can go. Okay, so there's much more structure to capture, kind of, with rotations. So that's what we're going to look at today. And we'll settle on an initial way to handle and describe an arbitrary rotation of 3 dimensions. Okay, but it is quite complicated, and there are many different conventions, or there are many different approaches or systems for describing general rotations of 3-dimensional space. So it can be tricky. Okay, because different sources that you look at will be using different systems and different definitions and so on. So anyway, so let's just start with some basic matters. What coordinate system are we going to use? Well, we're going to use the usual X, Y, Z coordinate system. Okay, but remember when we introduced this in chapter 1, key point was that the XZ plane is usually thought of as the horizontal ground plane, and Y is the vertical axis. Okay, that's the convention that's used in computer graphics. Okay, this is because computer graphics started off as being 2-dimensional, and traditionally then their X was used as the horizontal axis on the screen, Y was used as the vertical. So when with the addition of a third, Y was used as the vertical. So the typical view of a scene would be to have the ground here and the vertical direction corresponding in the real environment to be up the screen. And so when you extend your system to 3 dimensions, for reasons of kind of consistency, they wanted to keep that. So they kept Y as being the vertical axis in the 3 dimensions. So XZ is the horizontal plane. And remember, we're using a left-handed system. So you think of your thumb and 2 fingers on your left hand. The X, so it goes the thumb, first finger, middle finger, X, Y, Z. So the XZ is the ground plane. So you normally think of it oriented like this. X, my thumb, Z, my middle finger, oriented like that. And then Y gives, my first finger gives the direction of Y, which is the vertical direction in the environment. We're thinking of this normal physical environment. Okay. So we need to remember that. And we should also be aware that there are other useful coordinate systems that in many ways it makes more sense to use for describing things in 3 dimensions, such as spherical polar coordinates or cylindrical coordinates. But because computer graphics always ends up somehow being, placing things onto the 2-dimensional screen, for which the Cartesian coordinates are the kind of sensible coordinates to use, because ultimately at the hardware level, the screen is just a rectangular array of pixels. Because things are quite tied into the Cartesian system on the screen, and also because we want a consistent way to represent transformations, we want to always represent them using matrices. And the Cartesian coordinates X, Y, Z are a natural choice for representing things using matrices. So for that reason, these other coordinate systems, while they are very useful for studying phenomena in 3 dimensions, spherical polar coordinates and cylindrical coordinates, they don't really make much of an appearance in computer graphics. Okay. So when we say R3 in these notes, we'll use R3 to refer to both the space of points and the vector space of all three-dimensional vectors. And we'll normally work with homogeneous coordinates. Whenever we're implementing anything using matrices, and whenever we're doing calculations with stuff, we'll normally be doing it using homogeneous coordinates. So a vector R is written like this: Rx, Ry, Rz, and its fourth component will normally be 1. And this would be the position vector of a point with the x, y, z coordinates Rx, Ry, Rz. Okay. Now, we normally keep the fourth coordinate as 1. If it ever arises that we're looking at a vector where the fourth component isn't 1, I mean, it will seldom happen. But in that case, then what we do to recover the actual coordinates of the point that this is the position vector of, we divide all the other components. We kind of renormalize the thing by dividing across by the fourth component so that it is 1. Okay. So if you're faced with a vector ABC3, the position, the point that would be the position vector of, under the homogeneous coordinates interpretation, would be the point with coordinates a third A, a third B, and a third C. Okay. Well, if you do things right, you shouldn't encounter that circumstance. Or if you start things off with all your vectors with fourth homogeneous coordinate 1, then they should always remain like that. Okay, so as I said, translations and scalings don't really present any more of a problem than they did in 2 dimensions, and we can dispense with those fairly quickly. So to translation, a translation transformation of R3, that's where you just take where you take all the vectors in R3 and you add some fixed vector to them. Okay, so this transformation, sending x to x plus d, where d is some fixed translation vector. Well, the matrix representing that under homogeneous coordinates is just the 3-dimensional version of the 2-dimensional translation matrix we already looked at. Okay, so it's this. You have the 3x3 identity block up here. You have the x, y, and z components of the translation in the last column, and then your last row is a 0, 0, 0, 1. Okay, so that's the translation matrix under homogeneous coordinates. Similarly, a scaling matrix, if you want to rescale all vectors by r, by some scaling factor r, then that will be represented by this scaling matrix here. So multiplying any column vector by this matrix S, that will have the effect of rescaling all the components by the factor r. Now that's where you're rescaling equally in the 3 coordinate directions. If you did want to allow different scaling factors in the different coordinate directions, so you want to stretch things out a lot, say in the x direction, maybe squash things down in the y direction, maybe only stretch them out a little bit in the z direction, then you could use 3 different scaling factors in those directions. And so you could use a more sophisticated scaling matrix S like this. Now those 2 matrices, of course, are where, if you think about multiplying any of these matrices by the 0 vector, by the vector representing the origin, you'll get the 0 vector back again. These are all scalings that are happening with the origin as the fixed point. So it's either shrinking things towards the origin or expanding things away from the origin. Now you could perform a scaling with some other point as the fixed point. So you could choose some point away from the origin and either shrink everything back towards that linearly or expand everything out from that point linearly by some scaling factor. So then you'd have to think about what the matrix for that would be. So there's a little exercise here, but I mean, we've already done matters. We've already dealt with matters like this, where things are happening away from the origin, and you want to express them using these transformation ideas, which you initially define as relative to the origin. So we could look at exercise 5.1 there. So it says, determine the matrix representing scaling by the factors Rx, Ry, Rz along the directions parallel to the X, Y, and Z axes, but centered on some other point with position vector C. Well, to express this transformation, we think about it broken down into 3 steps. Firstly, we want to translate R3 so that the vector C goes to the origin. Yeah. Then we'll perform a scaling relative to the origin using a scaling matrix that we've just looked at. And then thirdly, we'll translate back. So that this time now the origin goes to C. So step 2, we're still scaling R3 in the required way. But if you think of what the fixed point will be under the composition of these 3 steps, well, first you send C to the origin, then you scale relative to the origin. So the origin stays where it is. And then you translate the space again so that the origin again moves back to the point C. So overall, C will end up at the point C. So C is the fixed point of this process. So this will be the required scaling that's described in the question. So if step one has the matrix, well, this is going to be a translation matrix, and this will be Cx, Cy, Cz. In fact, not by those, I need to go by minus each of those. So I want to translate the space so that the point at position vector C goes to the origin. So I want to subtract the component Cx, Cy, Cz from everything. So this is where C is the vector Cx, Cy, Cz. So this thing is really, really bright. A bit less bright. So that would be step 1. Step 2, we would use a scaling matrix S. Well, this is really just the one in the question, or the one in the notes, Rx, Ry, Rz, 1, and zeros everywhere else. That's the scaling matrix. Scales the X, Y, and Z directions by these factors. Then what's the matrix for step 3? Well, okay, it's going to be the translation matrix with plus Cx, plus Cy, and plus Cz in those positions. Or for that, we can use the matrix that will be the same as the matrix T inverse. Okay, because the inverse matrix, this matrix T at the top is translation by the vector minus C. So to send it back, we just use the inverse matrix. So that will be the same as translation by the vector plus C. So overall, the matrix we want overall, so the composite scaling in the question then is represented by the matrix what's going to be the product of these, but just when you're writing down these composition matrices, just always be careful that you put them down in the right order. It's this which is applied first, then S, and then T inverse. So it's going to be T inverse S T. Because of the left-right convention, because we apply these matrices to column vectors which go to the right of them, you know, the order in which you write the letters down, if you're writing left to right, conventionally it's the reverse of the order in which the operations are applied. T, this is the one that's applied first to the vector, then the scaling matrix takes place, and lastly the inverse translation matrix, step 3, takes place. Okay. And if you wanted to have a look at the structure of the actual matrix, you could multiply all those 3 matrices out and have a look at the resulting one. Okay. Is that okay? Any queries about that? It scales this is going to scale. Well, it's just like it's described in the question. So C will, let's say the origin is at the corner of the room there where the walls and the floor intersect. The origin is down here. The position vector C is some point up here. So this is the matrix that will scale everything by the factors Rx, Ry, Rz. So they're the scaling factors in the directions parallel to the X, Y, and Z axes. But C will be the fixed point. So it'll if those scaling factors are less than 1, it'll be shrinking everything back towards C with the C point as the center. Or if the scaling factors are bigger than 1, it'll be expanding things out from the fixed point C, if you like. Yeah. But this is the way we're going to start to think about these processes. As we're not going to focus on the overall matrices themselves, but rather on the combination of steps. So to achieve something at a point other than the origin, the normal way we think about it is to drag that new reference point back to the origin, then perform the standard transformation, which is relative to the origin. Those have the simpler transformation matrices. Do the required transformation, be it a scaling, some kind of rotation or reflection. Do that relative to the origin. Then lastly, translate back. So you shift the space back so that the origin moves back to the original reference point. Then the overall effect of that will have been to carry out the required transformation. Okay. So, okay, I'll just go back to computer. No, if that's okay. Okay. Now, rotations are slightly trickier. Just because there's more space around us in 3 dimensions. There's more possibilities. So more things can go on, so it needs to be handled more carefully. So as we said at the start, a single rotation transformation of the space R3, this will be a rotation around some given axis. Okay, so there's going to be some line through 3 dimensions, and you're going to rotate the whole space by some angle around that line. Okay. Now, in general, that line could be any line in 3 dimensions. So in general, the line would be described by this vector equation of a line that we've seen before. So P is some fixed reference point on the line, and D was a direction vector for the line. Okay. So this vector equation describes the position vectors R of any point on that line L. So this would be the kind of data. P and D would be the data to specify L, and theta would be the rotation angle. Okay. So that's the kind of data you need to set up a rotation. But let's start with not trying to describe the general case, because trying to just describe the general case in one go is a bit formidable. It's a bit kind of undigestible. So we'll start with simpler ones. Let's think of some simple lines. You know, what might be the simplest lines to tackle first? Well, there's three obvious lines, and those are the lines given by the coordinate axes themselves. Okay, we're describing positions and components of vectors relative to the coordinate axes. So maybe the x coordinate axis, the y coordinate axis, and the z coordinate axis, they're the simplest ones to describe. Okay. So we can write down these three. So these are three rotation transformation matrices. They're using homogeneous coordinates. They're 4×4 matrices. And these correspond respectively to rotating space by an angle theta around the x, y, and z axes. Okay. So you recognize the kind of 2×2 rotation matrix that we met when we were looking at rotations of the plane. And it's just kind of inserted into this three-dimensional setting and now into the kind of four-component homogeneous coordinate setting. I said before that P, D, and theta were kind of the data to specify the rotation. Well, you do need a little bit more information. You do need to know by which sense you're doing the rotation. Is it anti-clockwise or clockwise? And you need to be careful about how you set up that convention. So the convention is that these are the matrices for rotating about by the angle theta in the anti-clockwise direction. But when you say anti-clockwise direction, you have to say in which direction you're looking, which direction you're taking that to be. So that's going to be when we're looking along the relevant axis back towards the origin from the positive half of the axis. Okay? So let's just draw a bit of a sketch to illustrate that. So in our left-handed system, oops, just like a little sketch of the three coordinate axes. So we take x and z as the ground horizontal plane, y is the vertical direction. We'll take x to be coming out of the board. And z to be going into the screen. So it's kind of something like, so this, my thumb is my x, my middle finger is the z, and my first finger is the y. So it's some kind of setting like this. The thumb is coming out, the z is going slightly into the screen, and y is the vertical axis. It's the left-handed system, remember. Left-handed system. So when we say rotate by an angle theta anti-clockwise, when looking back to the origin from a positive point on the axis, so that would mean that the matrix Rx that we just wrote down in the notes, that would correspond to rotating all of three dimensions by some angle theta. But look, theta is going in the anti-clockwise direction. Anti-clockwise direction around the x-axis as you look back to the origin from a positive point on the x-axis. So it's a bit of a mouthful, but, you know, to specify that. So we're looking back towards the origin from a positive point on the x-axis. So theta is the angle that's going anti-clockwise like that. Of course, if you looked at it from a point on the negative axis, you look at the same rotation, you see it going clockwise. This finger looks clockwise to me now, but it looks anti-clockwise to me then. So you know, there's so much room in 3 dimensions. You have to set things up carefully, and you have to specify things quite carefully to really pin them down. Okay. So you need to think about that carefully, and just be aware that you have to treat these things. Be aware you have to treat these things carefully. Okay. So we have these rotation matrices for rotating around the x, y, and z axes. Okay, that's good. If that's the kind of rotation we need, there are the matrices to carry them out. So that's fine. Now, you'll notice this negative sign on the sine trigonometric function is hopping around a little bit. That's correct. If you if you look at any of these situations closely, you'll see that this is the correct sign for, or it's the correct position to attach the negative sign onto. Yeah, maybe I should give you a little bit of detail on that, what I mean. So for instance, this, if you're doing the rotation Rx, really what you want to look at is the YZ plane. If you think of looking at the YZ plane, which is the plane of your middle finger and your first finger, Z and Y, and you're looking at it from a direction on the positive x-axis. So this rotation we're talking about is rotating that way by some angle theta. So the vectors j and k, remember the I, j, k go in the x, y, z direction respectively. The starting off vectors, that's the starting off position of the vectors j and k. J going in the y direction, k going in the z direction. Under rotation, they change to something like this. So this is rxj, and this is rxk. And just for reference, we can plot it in their old directions there. So you see that you see Rxj now, if you just look at the sign of the components of Rxj, it's still got a positive y component, but it's now got a negative z component. So it's pointing off over here. And that, you can see this here. It's still got a positive y component, but it's got a negative z component. And the components of Rxk, the image of k under this rotation, well, they're going to be positive z and positive y, which you can see here. Positive y component and a positive z component. Okay. So you can draw a similar picture for the other. If you look down on the x, if you look from a point on the y-axis, so this one is now corresponding to this, and look down onto the xz plane. So use your fingers to figure out what it's going to look like. You're on a positive point on the y-axis. You're at the tip of your first finger, and you're looking down onto the xz plane. So x is going to come out to the right, and z is going to go up. And when you're rotating around the z-axis, you're looking at x and y from a positive point on the y-axis, on the z-axis. You're looking back here, so you see x is actually x, y. So you're actually, x is coming up and y is going out to the right. This is the importance of using the left-handed system correctly instead of the the right-handed system. There's nothing, you know, you could set out from the very beginning and use the right-handed system, but the plus and minus signs in all of this would move around slightly. So it's important to stick to whatever the convention in play is. So this one looking down on the y. Yeah, so this would be the angle theta here. And then this would be the angle theta here as well. So if you look at, analyze the behavior of the vectors under these rotations, well, you'll satisfy yourself that these rotation matrices are the correct ones. Now these matrices have, are these basic types of rotations, there's some interesting terminology attached to them. And that's the terminology of roll, pitch, and yaw. So these terms come from aeronautics. These are the terms that are traditionally used to describe the state of an airplane. Most of the time, you want your airplane flying kind of horizontally in some fixed reference direction. But when the airplane undergoes some kind of a change, it either does a roll. So find the, you know, my hand is the plane going that way. A roll is to, you know, go like this, left to right, and everybody falls over to the left or right. A pitch rotation is to go up or to go down. And lastly, a yaw rotation is to kind of change the direction that the plane is going. So if the plane undergoes a yaw rotation, everybody on the plane is still standing upright, okay. But if it rolls, you roll to the side. Or if it pitches, you either pitch down or pitch up like that, okay? So now how does that relate to this? Well, if you think of if you position the plane so that it's flying in the XZ plane and it's flying in the direction of the Z axis, this is normally the convention. Think of that plane flying in the direction of the Z axis. So if you could augment this image here to have Z as the Z-axis, that's the direction the plane is going. X would be the pitch axis, and then Y would be the yaw axis. Although I wonder, that might be the left or the right-handed system. It's possible that that's the right-handed system. This is another complication that in other fields apart from computer graphics, it's more traditional to use the right-handed system. So in computer graphics, we use the left-handed system. Sorry? Fleming's, are those from like electromagnetism for it, only that it's, well, that's something to do with in 3 dimensions, isn't it? The way a magnetic field is oriented around a flowing current. So yeah, so you need these conventions to tell you, or these rules to tell you what the direction of the magnetic field is relative to the direction of the current, because there is 2 possible senses it could have. It could be going around that way or that way. Yeah. 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 And you had to use the right one, or otherwise you got things going in the wrong direction, or you got the positive magnetic pole mixed up with the negative one, or vice versa. Yeah. Yeah. Okay, so we may come across these terms roll, pitch, and yaw. In a computer graphics sense, the roll is with respect to the Z-axis, the pitch is the X-axis, and a yaw rotation is relative to the Y-axis. Okay. Okay, but that's fine for those standard types of rotation. But those aren't all the rotations that there are. We need to be able to work out how to describe a rotation about any axis whatsoever. Now, what we don't attempt to do is to give some formula for what the matrix looks like, given remember this would be the line L, which has got position vectors p plus lambda d, and we want to rotate by a certain angle. We want to rotate by a certain angle around that axis. One approach we could do is to just write down some giant matrix which has inputs p, d, and theta into it, which would be the rotation matrix. But it would be a bit of a mouthful. It'd be quite big. There'd be lots of terms everywhere, and it'd be very difficult to see what's going on, and probably impossible to remember unless you had a very clear photographic memory, and very hard to see what was going on, very hard to understand or appreciate why that was the correct matrix. So the approach we take, rather, is to try and describe rotating about that line with in a combination of steps, as a composition of a certain number of steps. And very similar to the example that we just did with the scaling, where first of all you drag everything back to the origin, then scale about the origin, and then send everything back to where it's supposed to be. Well, we do that same thing with rotation. So if I want to rotate around L by an angle theta, I'm going to do some setup steps first. Now this line L mightn't be going through the origin. It might be completely missing the origin. So the first step I'm going to do is I'm going to translate the whole of space so that I drag L back so that it does go through the origin. Okay? So I could do that by translating by the vector minus p. That would bring L to be a line that does go through the origin. That would bring you to some setup like in figure 5.3, where now I want to rotate around the vector d by some angle. But d is not in any one of the x, y, and z directions necessarily. But what I'm going to do is I'm going to arrange that it is. Okay. So having translated the space so that I can now focus on d coming out of the origin, I want to rotate around the axis d. I do some setup steps first of all. First of all, I now rotate around the y-axis. I do a yaw rotation. Remember, rotating around y is called yaw. I spin the whole of space around the y-axis so that this triangle here, d, dy, and this projection of dv, I send all that so it's sent to the yz plane. So I do a yaw on this, which is a rotation about the y-axis so that the situation reduces to d being a vector in the yz plane. Okay. I then do a pitch rotation. So that d is now I'll just do it heavy there so it stands out, because it's now aligned with the z axis. Then at this point I do the rotation by theta. At this point I do the required rotation by theta about the d axis, because d is now aligned, sorry, rz. D is now aligned with the z axis. So now I do the actual rotation that was described originally. So that achieves the rotation by theta, but now everything is out of place, so I need to put everything back again. So I do the rotation by theta, and then I reverse the pitch, I reverse the yaw, and finally reverse the translation. So those steps are summarized. So then just I reverse the pitch, yaw, and the translation. It's just a quick summary with some sketch diagrams. So these are the steps. First, you perform a translation to bring L to go to the origin. Perform a yaw rotation followed by a pitch rotation so that the rotation axis L is now going along the z-axis. You then rotate by the required angle theta about the z-axis. And then do the inverse pitch and yaw, and then do the inverse translation. And the composition of all those steps then will be the required rotation transformation. Okay. So now when I see you on Friday, we'll investigate this, and we'll look at an example of this, and we'll gather all the matrices for the individual steps, and we'll look at what the general product matrix comes out as. Okay.